talk about explicit solutions of differential equations, so now I'm going to talk about implicit solutions of differential equations. For an explicit solution, I had a function that I could just stick into my differential equation, but implicit solutions are relations instead of functions. So it could define one or more explicit functions on a given interval. So let's look at some examples of these. For my first example, my differential equation is dy dx equal to 3x squared over 2y. And the relation that I want to check is y squared minus x cubed plus 8 equal to 0. And I'm particularly interested on the interval from 2 to infinity. So the first thing we're going to do is try to solve this equation over here for y. And when we do, we get y is equal to plus or minus the square root of x cubed minus 8. We're going to need the derivative of this, so let's go ahead and take the derivative. Using the chain rule that we get the derivative is plus or minus, depending on if we had a plus or minus to start with. 3x squared over 2 times the square root of x cubed minus 8. Let's start by checking the positive value. So the differential equation says the derivative, which we just found, should be equal to 3x squared over 2 times y, which we had solved for previously. And we can see that this works. The 2 to infinity just implies that the square root is actually defined, that we don't have a negative underneath the square root. And similarly, you can check the negative side and show that it works as well. My next example, I have, for my differential equation, 1 plus x e to the xy times dy dx plus 1 plus y e to the xy equal to 0. And the relation that I want to check is x plus y plus e to the xy equal to 0. And we can see that this one's much more complicated. In particular, I can't solve this equation for y like I did on my last example. So instead, to try to find the derivative, let's use implicit differentiation. We start by taking the derivative of x, which is just 1. We then have the derivative of y, which is just dy dx. And then we need to take the derivative of e to the xy. Well, the derivative of e to the x is e to the x, so we start with that. And then times the derivative of the exponent. For the derivative of the exponent, we're going to have to use the product rule. The derivative of the first times the second, the derivative of x is 1, times the second is y, plus the first times the derivative of second, so x times the derivative of y. Finally, we need to take the derivative of the right-hand side, which is just 0. So this thing looks really complicated, so let's see if we can simplify it a little bit. So I'm going to start by distributing the parentheses, and then I'm going to group the dy dx terms. I had a dy dx and an x e to the y dx, so that gives me 1 plus x e to the xy times dy dx. And we can now see that this is just our differential equation again. So this has to be an implicit solution on some interval, because whenever we took our derivative, we got back to our differential equation. And the relation that I'm looking at is 4x squared minus y squared equal to c. And I'm going to do this the same way I did the last example, through implicit differentiation. We start with the derivative of 4x squared, which would be 8x. And then the derivative of negative y squared is negative 2y times the derivative of y. On the right-hand side, c is a constant, and the derivative of any constant is 0. I'm now going to divide everything through by 2. That gets me 4x minus y dy dx equal to 0. And we can now see if we just multiply through by negative 1, I do get back to my differential equation. So therefore, this must be an implicit solution.